In this video we're going to learn about a transistor property that's used to describe the effect of transistor capacitances. The property is called the transition frequency, or Ft, and it's a commonly reported measure of how fast a transistor can go. So Ft is a type of speed limit that's reported for transistors, but it's a bit of a weird one. It's the frequency where the transistor's current gain drops to 1. So I've drawn a schematic on the left that we can use to measure the current gain of a transistor without any external elements or loads messing with our measurement. That's why I chose to bias it with a current source. We can draw the small signal circuit to set up our current gain calculation, and note that I've shorted the output to ground because current gain is measured by calculating current through an output short when you're driving with an input current source. And that's the same as saying we test current gain with Rs equals infinity and RL equals 0. That short at the output lets us simplify the small signal model quite a bit. RO is shorted on both sides, so I've removed it from this simplified schematic. And CMU is grounded on the right, so we just put it in parallel with CPi and RPi. The current through the output short is equal to the current in the GM generator, which is given by GM times VB. And then I substitute in for VB by multiplying the input current by the input impedance. So we have the input current here times the input impedance, which is RPi in parallel with the CPi and CMU combination, the parallel combination of those two caps. Rearranging a bit, we get that current gain is equal to beta at DC, which makes sense. And that it rolls off as a first-order system at higher frequencies. The corner of that first-order system is determined by RPi interacting with the parallel CPi-CMU capacitor, but I've chosen to rewrite RPi here as beta divided by GM because that suggests an approximation. If we pretend that the first term of the denominator is bigger than this 1, then we can say that our transition frequency our corner frequency is going to be where S exactly cancels out this CPi plus CMU over GM term. And that's at the frequency S is equal to GM over CPi plus CMU. So GM over CPi plus CMU gives us our corner frequency in radians per second, and our transition frequency, or Ft, is given by 1 over 2 pi times that, to express it in hertz. I've mentioned a few times that Ft is weird, and one way it's weird is that it weighs CPi and CMU equally. They're just added together to make the denominator. In practice, you often need to design much more carefully around CMU than CPi, even though CMU is smaller. Ft also isn't the ultimate speed limit of a transistor because you can still amplify signals, even if you can't amplify current, because maybe you're driving that current into a big impedance or something. So your voltage gets bigger. So there's a separate measure called Fmax, which measures the frequency at which your power gain drops to 1, and Fmax is a much more serious speed limit than Ft. But even in spite of those quirks, Ft is reported quite often, and it's useful to be able to read it off data sheets and convert it into capacitances. So in summary, the transistor current gain is 1 at Ft. Ft is given by this expression. And this current gain test that we use to find Ft weights CPi and CMU equally for better or worse, and Fmax is the frequency where power gain becomes 1.